climate. Please join me in congratulating and welcoming Peter for this award and for his gracious acceptance of our invitation. So I'll let Peter take over.
Thank you, Megan. This happened because I gave this talk a couple of months ago in university, and everybody was in Washington, so they asked me to come do it here. I did push the button to change. Oh, maybe I do this. No, it is. Oh, okay. So let me give you the basic idea of where I'm going with this. You'll find that I give a long introduction, and then this is a bit of a polemic, as I think will become clear. But we imagine that all of our sciences, we have a crust which is less dense than a mantle lithosphere, which is slightly more dense than the asthenosphere, at least if you put them at the same pressure. And most mountain ranges are built by shortening the crust and the mantle lithosphere horizontally, so you shorten that, thicken the crust. This is standard freshman geology. Isostasy, if you have a high terrain, you'll have a crustal root that balances that. But you have to do something with the mantle lithosphere. And when Airy, 150 years ago, realized that you had to have isostasy with thickened crust, he didn't know anything about the mantle. You have to thicken the mantle lithosphere, so you push down dense material, you thicken the dense material. So that actually pulls the surface down a little bit. And you can imagine as well that this is more dense than the surrounding material, so this sets up an instability where this can sink and go away. So over here, this pale blue is meant to be what's been removed. You take a load off. This is like throwing stuff overboard on a ship. The ship comes up, surface goes up, the moho goes up. When you do that, you put potential energy into the system. That potential energy, in fact, can ultimately be used to push the mountain range apart, maybe with thrust faulting still on the margins, but anyhow, you can induce divergence in here. Now, the basic idea that underlies this, and I would say is the most fundamental concept we have in all of tectonics and certainly crustal dynamics, is isostasy. It's Archimedes' principle. And there are two variants of this. Airy recognized this in 1855, I think he published this. If you have a high range, you've got to compensate in some way with a less dense material. So in this case, the crust thickens and you have a crustal root. In fact, what Airy did was he read a paper by Pratt. Pratt had shown that the surveys that Everest had carried out across India in two ways, ordinary geodetic surveying with a theodolite and measuring across, and using astronomical techniques, were both good, but they differed from one another in an important way, and Pratt didn't understand this at the time. But he presented all this good data, sent it off. He lived in India, sent it off. Airy read the paper and thought, oh, yeah, of course, this must be what's going on. Pratt, apparently, I haven't confirmed this. I haven't found a way to confirm this. But apparently, Pratt wasn't very happy about this. So he came up with an alternative idea, which is that not that you don't have thickened crust, but you have laterally varying density across the region. So this would be a column of less dense material than a column over here. And being less dense, it would stand higher. And in modern understanding, the way to make it less dense would be to make it hotter here. So you have hot material here, cooler material over there, and you'd stand high, but the crust itself would have the same thickness in this case. With these, Airy isostasy seems to account for high terrain in most big belts, high plateaus like Tibet or the Altiplano. But Pratt isostasy counts for the depth of the ocean floor, shallow ocean floor, mid-ocean ridges, and spreading away. High areas like East Africa, the Basin Range, I think, and I'm going to argue the Southern Rockies as well. Okay, let's look at the Rockies. I use this to set up an example of a. Oh, what happened? Did I do that? Oh, sorry about that. So here's a map showing Western North America. Plains out in here, plains coming up into the Rockies Front Range, and here going west through the Rockies, the Basin Range province further west. This gently sloping down to the east. You know this. If we look at results, these results I'm showing you here, done by Ann Sheehan, Jeff Abers, Craig Jones, and Art Lerner Lamb, back now years ago. This is a plot of the average elevation on this axis going from the plains, obviously 1/2 kilometer high, versus the moho depth, the thickness of the crust over here. Now, ordinarily, if you had airy isostasy, you'd have a linear trend going through this, because as you raise the height, you'd have to thicken the crust. And you don't see that at all. They didn't bother to do a least squares fit on these data, but the answer would be clearly something close to 0. There's no correlation at all of crustal thickness with height. So one would have to conclude that airy, in this case, Airy's isostasy does not work. Now, the tool that I think is most useful for looking at a lot of what I'm going to talk about is gravity anomalies in here. And what's plotted here is topography. High areas are red, decreasing to the east. Plotted over here are isostatic gravity anomalies. These are the gravity anomalies that measure gravity at the surface of the Earth, correct it for everything you correct for, but also assume that you're in isostatic equilibrium and correct for that mass beneath you with an assumption. And what you find is these are very small. These are around 0. All the yellows are around 0. 30 milligauss is a big number on a scale like that. There are a few places where you get bigger numbers, the mid-continent gravity high in here. Some of the mountain ranges, the bighorns, the wind rivers, but very narrow belts. And my guess is if one corrected it in a different way, you could get those to go away. So the point is there's no excess or deficit of mass under these ranges, as either Airy or Pratt would have said, though Airy would have had it wrong in this case. Going further, using the same seismological study that Ann Sheehan and her colleagues had used, Lee and Grand looked at S-wave delays, concluded the average shear wave velocity in the upper 200 kilometers is 9% greater beneath Kansas than beneath the Rockies. 9% is a big number. You don't get much bigger than that. And they conclude a hot mantle beneath the Rockies implies the mantle density is low. High topography is at least partially due to a buoyant mantle. I would argue entirely due to a buoyant mantle. Well, that's where things were 20 years ago. I think that's kind of where things were before 20 years ago. But now, so this is Pratt isostasy. What else? Now where are we? I would argue we're in exactly the same place, just we've changed the terminology. So now it's dynamic topography. This talk is going to be a diatribe against dynamic topography. Warn you in advance. So we have a paper published just a couple of years ago, Mantle-Driven Dynamic Uplift of the Rocky Mountains in Colorado Plateau. And here's a plot. The crust is shown on top with the blue line marking the moho. It's not meant to mark the moho, but that's where it is. No variation in crustal thickness. The reds, the warm colors, are showing low wave speeds, presumably because the region is hot. The colors, as I recall, are P-wave speeds. The contours are S-wave speeds. The lowest S-wave speed in here is in the middle. So the results are the same. There's no variation in crustal thickness to speak of, but there's a hot upper mantle beneath the Rockies. What's happened is we now have mantle-driven dynamic topography. Okay, dynamic, read it again, mantle-driven dynamic uplift. So I want you to ponder a concept. A car is parked on a hill. Who or what drives it? I'm arguing this because the Rockies are parked out here, and they're not driven. They're just sitting there. It's like the old joke of you go to Maine and ask the Mainer, where's that road go? And he says, don't go nowhere. It just stays right where it is. Well, that's true of the Rockies. So what drives a car on a parked hill? Sorry. What drives? Gravity. Gravity pulls it down. The brakes prevent it from going down. Is that a driver? The driver slipping the clutch. A big stone behind the tires, that prevents it from going down. And this is one that I happen to have some experience with. Anyway, that was before I got a driver's license when he did that to me. Okay, so the point is, of course, that nothing's being driven in dynamic topography. In that case, it's merely changing the words. You know, it's like all the politics, you change the words and you persuade people that something's new, but it's all staying the same. Okay, now here we have another recent review paper by these fellows here, published last year, Dynamic Topography. These are global maps, their version, one by Steinberger and so forth, various versions. And you might say, well, they all look sort of alike. It's red out here over the Pacific in all cases, different shades of red. I contend, yeah, they might look similar, but everyone claims at least 1,200 meters of dynamic topography, but they differ by at least 1,000 meters. So actually they don't really agree with one another. If you're willing to say 1,000 meters doesn't matter, okay, well, you shouldn't bother even stay in the room because I'm going to insist that that's a big amount. But you might say, well, but they are similar. They're all seeing something similar. And those of you who are studying this similarity, I got a bargain for you. These are similar, and this is negotiable. I'll offer 10 of these for one of them, but you know, if you want to, anyway, they may be similar, but they're not alike. Okay, where does dynamic topography come from? Actually, it goes back. It's got a good, solid root in a magnificent study by Hager, Clayton, Richards, Comer, and Jablonski, published nearly 30 years ago. And they actually were looking at topography on the core mantle boundary, not on the surface, but that doesn't really matter. One has a geoid, an old geoid back in those days, where you have positives in some regions, and you have negatives up high, negatives in other regions. And they also, particularly because Clayton, Comer, and Jablonski were seismologists, they knew where you had high speed and low speed in the deep mantle. And where they have high speed, you'd say, well, that means it's probably a little colder, it probably means it's a little denser. So if you make that assumption and you put that in, you find out in here that in fact, this is low speed material out in here, it's low speed material. You would predict that you'd have a geoid low. You'd predict you have a deficit of density, and you'd predict not what you observe, but almost the opposite of what you observed. And they argued, well, that's not what's going on. The density contrast at the core mantle boundary is huge, and if you have low density material down in here, what it does is it rises and it draws the core mantle boundary up, so you actually get excess mass down in there because you raise that surface. So when one allows for the dynamics, one actually gets a good fit. When I don't show it to you, but one can match the positives where they're positive and the negatives where they're negative. This would be the effect of dynamics, in this case, operating on the core mantle boundary in particular. Well, so that was the first use of the term dynamic topography that I've found. But Hager and Richards wrote more good papers on this subject, but they did stick a sentence in, and in the parentheses, these are their parentheses, mid-ocean rises, which result from cooling of the upper thermal boundary layer, indeed, in deep sea trenches, are familiar examples of convectively maintained topography. This has been taken to mean that these features are part of dynamic topography, and many people would argue they're part of it. Well, this is going too far, because we don't need to understand mantle convection to understand the depth of the ocean floor. We don't need to do that. And as scientists, of course, our goal is to understand. So if all we're trying to mimic with some fancy model, well, let them do it. But the goal is to understand. Do we need to understand convection for this? No. All we need to know is that there's thermal contraction of a coulee plate of lithosphere, and it's in isostatic equilibrium. And underlying all of what I'm going to talk about is that this is the reference state that we should be considering, and the Earth doesn't depart very much from that state. Okay, well, that's one view of dynamic topography. Here's another. This is another review paper. There it is, written right there. Jean Brown is a very good geodynamicist, Belgian living in France. And I quote from a part of it, I think the abstract. Significant portion of the Earth's topography results from the viscous stresses created by flow within the underlying mantle, rather than by the moving plates. This dynamic topography, that's how he's defining it with those words up there, is transient, varying as mantle flow changes, and is characterized by small amplitudes and long wavelengths. And small here, small amplitudes, we're talking hundreds of meters, not lots of hundreds of meters, a few hundred meters. This is quite different from kilometers that some of the others have said. So we have, whoa, what am I doing here? Am I pushing a button? Maybe I'm pushing a button I shouldn't push. I may be. Well, I'll tell you where I'm going while it comes. There. So we have Hager and Richards, their definition, most long wavelength topography, and large amplitudes, thousands of meters. To be fair, they said only 1,000, but others have gone beyond 1,000 in here. And you know, I wonder if I'm touching. Oh, maybe that's what I think I'm pushing the wrong button. It's, of course, my fault. Okay, Brown said it's due to flow-induced stresses, which are small amplitude, hundreds of meters. And so if one think I pushed this, and there we go. So how do they differ? Well, topography, dynamic topography, according to Hager and Richards, is isostasy plus this dynamic topography that Brown uses. And this is the big part. So, so this little simple equation expresses what we're talking about. Now, I'd like to give you an analogy that bears on this, I think. Dynamic topography and isostatically compensated topography. Hager's definition of dynamic topography includes all of this. Well, if you know relativistic mechanics, you know all of Newtonian mechanics. And there are probably a couple of you in the room who need to know relativistic mechanics. Tracking satellites, you have to know that. Most of you don't. And I would argue most of you don't need to bother with that. This is good enough for most of what we do. So this is my analogy. I want to drive this home a little harder, though. You're out in the desert, your car breaks down, and you need to find a good auto mechanic. And how would you choose a good auto mechanic knowing what we know about mechanics? I think the answer is obvious. It would be whether he or she understands Einstein's theory of relativity. That's the criterion we would use, at least if we take dynamic topography seriously as well. Okay, well, I haven't really gotten to the problem. You have a choice between these two, but that's not really what the choice usually is. Most dynamic topography is merely the output of some complicated realistic model, which the authors probably understand, though that's not always obvious. But it's hard for the rest of us to understand. And so now I'll give you a little philosophy. Dan McKenzie, one of the people who first recognized plate tectonics, the early founders of plate tectonics figure importantly in this talk. The trouble with most people in this business is they think that because they have a bigger, faster computer, they can make more complicated models that are more realistic. Hit that too hard. They should realize that because they cannot solve the equations, they're stuck having to use the big machine. Dan has never used a swear word in my life, but I think if he could, he would. He'd put it in there. They must make the model simpler if they want to understand the results. Now, understand is a key word because as scientists, we're always trying to understand. We're not trying to make things look like something else. Okay, here's an example of where dynamic topography is popular. Southern Africa stands about 1 kilometer high, wide, 2,000 kilometers in dimension, stands 1 kilometer above sea level. Is this dynamic topography? And the consensus of many authors is yes. The logic is that if you look in the lower mantle, this is now a tomographic image of the lower mantle, where the warm colors show you low speeds. So you have low speeds under Southern Africa, near the core mantle boundary here, and just above it, 850 kilometers shallower, you still have that. Cross sections, this cross section east-west across, warm material rising in some way. Another cross section, low speed, presumably warm material rising, another cross section, the same thing. The logic is that this is pushing the surface up. So as I said, widely believed that there's dynamic topography over Southern Africa. Now there is a bit of a very difference in opinion. These folks want 1,200 meters. These want 700 or 900. You know, if you're not too concerned, you could say, well, 1,200 isn't very different from 900. So they want 700, 900. This is 650 to 700. Well, 700, they're equal. 650 is just a little more than 600. So these are almost equal, and they come down. So really, there isn't much difference in all these, right? But I hope you'd all agree that the one fact that we would all agree on is that they can't all be right, that these numbers are different from one another. And we're quantitative scientists, and we do worry about whether two numbers are within uncertainty of one another. Okay, I'm going to take this with a very simple, look at this in a simple way. Stokes Theory, a sphere sinking through a viscous fluid. So you imagine a sphere sinking through a fluid, or if you like, the fluid wrapping around its sides. It's not accelerating, it's in a balance. You can solve for the speed. This is a hard problem. Stokes solved this almost 150 years ago, but it's hard mathematics. The speed depends on the square of the radius, not the cube, the density difference, gravity, and inversely with the viscosity of the surrounding fluid that's wrapped around the sphere. And some of this makes sense. Obviously, the more dense the sphere, the faster it'll go. Obviously, change the sign, it'll go up or it'll go down depending upon the sign of this. Depend on gravity, put it on Jupiter, it'll go faster, and it'll depend on the viscosity. You drop something into honey, it sinks slowly. You drop it into water, and it sinks more rapidly. Well, what Jason Morgan did Jason Morgan, the other person who discovered plate tectonics, back before he did that in 1965, is he looked at this problem, but with a roof on the top. He says you don't have a full infinite space, you have a half space of fluid. You have a sphere in here with a radius A. This one we're going to make it less dense so it rises, and it deflects the surface. It rises with a speed that looks like Stokes' speed, but it's corrected because of the influence of the sphere. E is the ratio of the radius of the sphere to the depth of its center, d being this distance down, and the radius being this quantity right here. So you get a series expansion in here. But you can solve for everything. You can solve for all of the fluid flow, the stream function, the strain rates, the stresses, the whole works. And when you do that, you get a normal stress at the surface consisting of both a perturbation of the pressure and a deviatoric stress. Some of these signs may confuse you because here compression is negative. This will depend on the density. It will depend on what we had before. But notice now we have a radius cubed, and then we have some geometry, including the depth in here. And we can calculate that stress acting on the surface, assuming the surface doesn't move. Well, we can deflect the surface, raise it a small amount, delta H, and that will be balanced by that normal stress at the top. And I put a density of the mantle in here, assuming that the whole crust rises. The moho goes up, not just the crust itself. So the density that's important is the mantle density. And then we can do what geophysicists often do. We have an equation here. We can invert this equation. This is a difficult operation. We divide through by rho g, and we get the height of the surface. It varies in this way. It varies with the mass of the sphere, because remember the delta rho times the cube of the radius of the sphere, except for a 4 pi over 3 factor, is the mass of the sphere. It depends inversely on the mass of the material you're lifting, and it has a bunch of geometry that in principle we know. And I should say this is an approximation because we've only carried out a certain number of terms. Okay, notice that this is independent of viscosity. I leave that for you to think about, but that makes sense because the rate that the sphere moves depends on the viscosity, but the stresses also depend on the viscosity and cancel out when you compare them. Okay, gravity anomalies now provide a test. There are two mass anomalies that contribute to a region that has a sphere rising underneath it and the surface that's been deflected. First, you have from the mass of the sphere. We go back to Newton. Newton would say it's Newton's gravitational constant times the mass of the sphere divided by r squared. But when we measure gravity, we measure the vertical component. So we need to take into account a bit of trigonometry in here. It scales if we're really far away. If r is way out to the side, out in here, we get a smaller component for the same depth because the component of gravity, the vertical component, is smaller. So we get a number, and there we have basically the mass of the sphere with a depth and with the radius scaled in there. We also have the topography. From the topography itself, again, this is very simple. Multiply 2 pi g times the mass anomaly times the surface height, and we get an expression that looks like this. You'll notice the same mass of the sphere, 4 pi a cubed delta rho divided by 3 is the mass of the sphere times Newton's constant times some geometry. Well, if we do this for some sensible cases thinking about the lower mantle, so the lower mantle, we're going to have D be large, 1,000 or 2,000 kilometers. We need a sphere that's big enough to give us a surface deflection that's big enough with a density anomaly. So we let the sphere have a radius of 500 or maybe 1,000 kilometers up in here. And we consider only cases where we have 1,000 meters of surface height because everything scales linearly with this. And then we get a distribution. We get a distribution of surface height. Obviously, a small sphere at a shallow depth gives you a more localized elevation profile than one that's steeper. And we can calculate gravity anomalies. Same thing. Again, using that height up in here, the free air gravity anomaly, maximum over the sphere, of course, decreasing rapidly when the sphere is small radius and shallow depth, falling off more rapidly when it's deeper, regardless of what the diameter is. We can do that, but notice these values. In fact, the next slide takes you through them. If we just look directly over the sphere, calculate gravity, we get a negative anomaly due to the mass deficit in the sphere, 46 milligauss. It's not a small number in gravity. But the surface topography, 1,000 meters, will get us 138 milligals. Of course, we all know how to add a negative number to a positive number. The gravity anomaly should be 92 milligals for this particular case. If the surface is a kilometer high and it's deflected by stresses that arise from something like a sphere, it doesn't matter what the shape is, rising in the lower mantle. So we can look at the real world. This is now a map using from the GRACE mission, looking at the whole of the world, but let's just blow up Africa over here, and you see gravity anomalies over southern Africa in the yellow in the 20 milligal range, maybe stretching in a little bit over here, which no isostatic correction has been made to this, stretching up close to 40 milligals, but gravity anomalies that are less than 30 milligals. Well, what do you predict for the cases where 1,000 meters was 92 milligals? Well, 1,200 meters will be 110 milligals, and I give you a bunch of numbers that get down into this range, simply depending on the height of the region. And those calling for gravity anomalies greater than 30 milligals clearly fail. The data from Africa really show that's the case. So let's get rid of them. So those are gone. So I do run into this problem of what do I do? So I got rid of only part of this study, so I took the et al. Out in here. But I could have done it another way. Actually, he is a co-author up in here, so he's already been taken out in another way. Okay, I digress just a little bit. Looking at the whole map of the gravity anomalies, again, most of the world, you're in this range of plus or minus 30 milligals. You have some examples, and these are topographic effects. This is not mass deficits when you get into these areas. Most of the world, I would argue, is most of the world gravity anomalies deviate from those expected for isostatic equilibrium by no more, only in rare places by as much as 30 milligals. This isn't a quantitative look, but that's what I take from, what did I do? Shoot. Nope, I'm going good. Whoa. What am I doing? You know? You think? I've got another one here too. Then we can really test it. It's possible that I've got some static. If anybody want to give me any static, already got enough. Suspense. No? There we go. Okay, so I'm contending that when corrected for isostasy, gravity anomalies are less than 30 milligals. Not everywhere, but almost everywhere. The fraction topography dynamically supported by devioric stress and flow-induced pressure, this is how Brown defined it, must be less than 300 meters. Okay. Going back to one of these studies, dynamic topography is that topography due to flow within the mantle, an idea that was first proposed by Peckeris. This is a beautiful piece of work. It is dynamic because the mass anomalies driving the density are moving. I urge you to ponder that, but anyway, I'm not sure I understand it. But this contrasts with isostatic topography in which the mass anomalies are in a state of quasi-equilibrium. I want to focus on that word right there, that word contrast, single it out, because what quantitatively is that contrast? In one case, it's dynamic. In the other case, it's not. It's static, and they contrast. But, you know, if they contrasted, and the contrast was the difference between a $1 bill and a $1,000 bill, you'd all agree it's important. But if they contrasted by a 1 cent next to a $1,000 bill, you wouldn't pay much attention. Okay, I'm going to now take you through a very simple case, going back to McKinsey. Again, one of the two people who gave us plate tectonics. This is after plate tectonics. Consider a simple situation. You have a half space and a surface temperature distribution. We're only going to worry about two dimensions, depth and the x coordinate, not worry about y. Or you just simply have harmonically varying temperature, kx, cosine kx. So it varies horizontally. We're going to allow diffusion of heat into or out of the half space. And when you do that, get a nice simple solution. It just falls off exponentially with depth. Z is positive upwards, so in all cases, Z is a negative number, so this is decaying. Hot, where you have a hot surface, you diffuse heat in, so it gets warm. Warm colors mean warm. Where it's cold, you take heat out, so you diffuse heat out, and it's cold, and you get isotherms like that. This is a problem that is easily solved. The next problem is less easily solved, but it's not so hard. I can do it. So McKinsey then said, well, let's make another assumption. Assume the viscosity is large enough that this temperature distribution can be sustained. You're going to keep that, but now let there be flow underneath. Then calculate the flow, the stream function, velocity stresses, and so forth. So you're assuming the flow is so slow that it's not destroying that temperature distribution. It's preserving that, but you're getting the pressure gradients that you would expect from that temperature distribution. Okay, well, big surprise here. This is a plot of the stream function, of the stream function, and the stream lines going around. Ascent under the hot area. You all should be surprised by that. Descent under the cold areas, both of them, symmetric. Divergence up at the top where it's hot. Convergence where it's no surprise in here. You'd all expect this. But now we can also calculate the topography. And not only that, we can calculate the topography due to different parts. The topography due to the deviatoric stress, this is the gradient in the strain rate times twice the viscosity, gives this yellow green line. That due to the pressure, there's a difference in pressure because of the flow. You know, a baseball curves because you have dynamic pressure. It's not quite the same, but it's similar to that. And you sum them, you get that number. Okay, this is a classroom. I read it out here. So you all came expecting a quiz. What would the topography be if it were an isostatic equilibrium? Or would the topography in isostatic equilibrium be larger than, smaller than, or equal to the dynamic topography? Now, I've done this in various settings, and I can assure you that, fortunately, in many of them, the smart person in the room got it wrong. So that should give you courage to take a guess. So I often start at one end or the other. So today I'm going to start. How many of you think the topography when you have isostatic equilibrium is going to be the same as what's shown here with that black line? Let me warn you that usually at the end of this, after asking all these three, I conclude that nobody thinks at all. Okay. So how many of you think, which will you choose larger, how many of you think that with isostatic equilibrium, the topography is going to be higher than it is? Aha, we have one. You sure? I know she's smart. No one wants to go with her. So that means the rest of you think that the topography is going to be smaller than in isostatic equilibrium. Is that the way you all feel? Or you don't think? Yeah, who thinks? Aha, okay, Freddie thinks it's smaller. Freddie's a smart guy too. I know Freddie. Good. Okay, great. You're wrong. It's higher. You get more topography when it's in isostatic equilibrium. And if you integrate the equations, I've given you what you need to know now. If you were to integrate the equations very quickly, you would know you'd get that answer for that. And if I had told you those, you would have gotten it. Anyway, so poses the question: dynamic stresses do not enhance topography; they limit topography. Right? I mean, do we have dynamic topography, or do we really have dynamically inhibited topography? As I said, this is meant to be a polemic or a diatribe. I'm trying to take this all the way down. Okay, there's one last... I got to give you a bit of truth in advertising, of course. Allowing an infinite depth of isostatic compensation is not what we usually do. Or the full depth of convective flow. That's not what we usually do. What we do is we assume that the isostatic compensation is the depth lies near the base of the convecting boundary or near the base of the lifter. So it's a bit of a cheat, but in fact the result is not unique. I'll show you an example in a second where we get the same answer. Okay, the last part of this talk is work that I actually was involved in. Greg Hausman and I did a study looking at dynamic topography of mountain belts. And what we did, this is a very idealized situation. Oh, I've got to give you a bit more philosophy. Right. Philip England. Usually they start with one thing they don't understand, the Earth. Then they make a model with a large number of parameters that are included in order to make the model realistic. But then they are unable to investigate the parameter space fully, and they wind up with two things they don't understand: the Earth and the model. And I contend this is a big step backwards. We haven't gotten anywhere when we do this. Okay, so we try to make it simple. It's still not that simple. So we have actually an infinite half space, but I'm just breaking it into a region where we have a crust on top, low density, a mantle lithosphere, and then beneath would be an asthenosphere that would have no viscosity. This would be inviscid down here. We're studying Rayleigh-Taylor instability. So the dense layer above the less dense layer is intrinsically unstable. So if we perturb the bottom of this layer a little bit, thicken the mantle lithosphere over here, it will sink. Thin the mantle lithosphere over here, it will thin because material will be drawn into the sinking area. So this is the problem we solve. But having put a crust on top, it's a different problem from what Rayleigh or Taylor considered and what most people have considered in the past. Okay, and I got to give you, no, it's the next slide. So the solution, the mathematical solution to this depends on 5 dimensionless numbers, depends upon the wave number of the perturbation or the wavelength that we put on the bottom. You can imagine putting any kind of wavelength down there, but the result will depend on that. It depends upon the ratio of the viscosity we use for the crust and for the mantle lithosphere. We're using constant viscosities to keep it simple. We have made it more complicated. We have 3 densities, a crustal, mantle lithosphere, and asthenospheric densities. So we have scaled, we have 2 density differences. We have 5 dimensionless numbers. Now, there is a precedent here. This is a quote that Freeman Dyson got from Enrico Fermi, and it's quoted in an article about Enrico Fermi by Dyson. But he says, I remember my friend Johnny von Neumann, one of the great mathematical physicists of the 20th century, used to say, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. Well, we aren't in von Neumann's class. We have 5 of these parameters, and we're not close to making the trunk wiggle, let alone understanding what he understood. But it turns out, really, the only numbers that matter very much or the only ones that matter very much because we don't know them very well, are the wave number or wavelength of the perturbation and the ratio of viscosity. And these are cartoon examples of 3 situations, one where the crust is much more viscous than the mantle lithosphere, one where it's much less viscous, and one where they're about the same. And what's plotted are deflections of the lithosphere-asthenosphere boundary down here, shown with this red line, and vertically exaggerated 25 times compared to the others. The MOHO, this is the bottom of the crust here. The MOHO is deflected, the green line. The surface of the Earth, the surface deflected with the yellow line. And when the crust is much more viscous than the mantle lithosphere, where the mantle lithosphere sinks, the MOHO, of course, goes down, but the surface goes down as well. Basically, you're just pulling this viscous layer down by the flow underneath, where the lithosphere-asthenosphere boundary thins, or rises, and the lithosphere thins, you push the MOHO up. You also push the surface up. At the opposite extreme, where the mantle lithosphere thickens and sinks, and the LAB goes down, MOHO goes down, but the surface rises just a little bit. And conversely, when you have rising flow underneath here, push the MOHO up, you actually thin the crust and you lower the surface a little bit. And you can imagine in the limit where this number would go to 0, you would have an inviscid fluid. The surface would never see what's going on underneath. You just deflect what's going down. The biggest surface topography we get is when the ratio is approximately 1. Then sinking pulls the MOHO down, but you draw material in and you actually thicken the crust and you get something that's like what Airy would predict, though I'll show you different. And where the MOHO goes up, you cause divergence of material, and the surface, in fact, goes down. They're actually accurately drawn, but they're a cartoon version, of course. So what are the relevant wave numbers? All this is done in dimensionless space, but we can put some numbers in. For mountain ranges, typically 150 to 300 kilometers wide, the dominant wavelength would be twice that, right? We're considering the crest as being a half a wavelength. So the wavelength would be 300 to 600 kilometers. The wave number, remember, is 2 pi divided by the wavelength, 2 pi divided by that number. The dimension of this wave number, we scale by lithospheric thickness, so h typically would be 100 kilometers. So if we put h 100, 150 kilometers, the important relevant dimensionless wave numbers are in this range of k prime 1 to 3. That will be clear in the next few slides. Okay. Okay, let's consider this case where the crust is much more viscous than the mantle lithosphere. Very viscous crust up in here. So sinking of the lithosphere-asthenosphere boundary pulls MOHO down, pulls the surface down. And this is how it depends on wave number. Remember, the relevant wave numbers are 1 to 3. So this is long wavelength over here, short wavelength. And we deflect the surface in a pattern that looks like that. Pull it down. Now, what's shown in the dashed line is the case that you'd get if you had isostatic equilibrium. If the surface were pulled down by a certain, if the whole column, if you took the whole column and calculated how much would it pull the surface down, it would pull it down more. So this is similar to the situation I gave you with McKinsey's calculation. The isostasy gives you a bigger deflection than when you have the dynamics. It's the same process, although here we do isostasy just with the lithospheric thickness, not all the way down. If one looks at the other extreme, where the crust is comparably viscous, less viscous, or even a bit more viscous, so this case where the crust and mantle lithosphere have the same viscosity, here where the crust is much less viscous, again, wave number here, deflection to the surface scaled to the LAB. The biggest one is for the case where that ratio is 1, biggest the ones I'm showing here. When this is very small, then you have almost no topography at all in this case. And if you then make the calculation for isostasy, those are the dashed lines, again, you pull the surface down more than you would, allowing for the dynamics. So the dynamics are contributing here, in this case, to support of the topography above. Now, the best way to look at this is with gravity anomalies. So gravity anomalies, we calculate gravity anomalies for the full dynamical calculations. Again, here's our viscosity ratio, very low viscosity crust. Viscosity here, where the crustal viscosity and mantle lithosphere viscosities are about the same. This one, where the crust is actually 10 times more viscous than the mantle lithosphere, and here, where it's 10 times less viscous than the mantle lithosphere. And of course, again, we compare this with the isostatic ones, Airy isostatic equilibrium, and we get all these positive dashed lines up in here. So the message here is that the dynamics are creating negative gravity anomalies for nearly all relevant wave numbers and viscosity ratios. Well, this is better studied actually with what's called the admittance. This is a concept that same McKinsey introduced. It's the ratio of the Fourier transform of the gravity anomaly to the Fourier transform of the surface height. It has a simple look, and it's remarkably simple in the Earth. You'd think this should have a phase, because these should both have phases, but for reasons, well, the Earth is good to us, there isn't usually a phase change. So just consider a simple problem of harmonically varying topography. The topography, the function of x, varies harmonically. The gravity anomaly will have the same signature. If you take the Fourier transforms of these, that just gives you a delta function, a spike at those values. But you divide one by the other, you just get a constant number. It's a simple relationship. That number right there is of order 117 milligals per kilometer of topography. If you have isostatic compensation, the deeper layer then gives you a quantity here, where Z0 is the depth, positive number. K0 is the wave number, again, used in this case. So your admittance at small wave number or shallow depth, when this thing is small, either that becomes 1, so you get nothing. Admittance will be near 0 at long wavelengths, small wave numbers, or shallow depths of compensation. But at great depths of compensation or high wave number, short wavelengths, this gets to be a large number, then that cancels out, and you have a 1 in here, and you go to this 117 milligals per square kilometer. Okay, well, what happens when we do this with our calculations? Well, remember, our gravity anomalies were negative, our surface topography is positive, so what we wind up with is a negative admittance, or a very small one in this case. The dashed line is Airy isostasy. It's positive. It's always positive. So dynamic stresses create negative or very small admittance in the relevant wave number range. This is a log plot here of the wave number, dimensionless wave number. But this range from 1 to 3 is in the log space from 0 to a half. So we're really looking mostly in this region. This case is going off scale, of course. And we're essentially always negative. Well, what about the real world? Well, admittance has been measured in many, many places. It's a way of studying actually another aspect of the lithosphere. But everywhere you go, the admittance is always positive. If you want to go back to dimensionless numbers, you do, wave numbers, you multiply that by 100. So this would be 1 on our previous scale, 2, 3, 4, 5, if you multiply by 100, going to the real world. Well, this makes life very easy because calculated admittances are negative, observed admittances are positive. Either we've made a terrible mistake or we've studied something irrelevant. And I think the latter is the case. Maybe it was a mistake to study it. But the dynamic contribution from flow-induced normal stresses to topography in mountain belts is negligible. That's the unavoidable consequence. We're predicting big negative numbers. We're observing big positive numbers. What we're predicting is based on something that isn't very important. Again, truth in advertising. This is a quote from a very nice paper by these folks who were actually studying Venus. Systems. Never mind. Fowler showed that in the limit of very large viscosity variations due to temperature, the stagnant lid of a vigorous convecting system is isostatically compensated, and topography can be calculated from the temperature profile of the stagnant lid alone, with only a minor contribution from the dynamic flow. So what I've been arguing, that's the point they're making, though that's not an easy read, I will say. Okay, so I'm just about at the end. How does mantle dynamics create topography? Well, convection moves mass anomalies to thicken crust. Airy was right about that. It does that for us. It also allows us to remove mantle lithosphere. The convective process removes that. You remove that, and the surface goes up. It does both of these. Moves big-scale convection, causes crustal thickening. Convective processes remove mantle lithosphere, but they do it in a state of nearly isostatic equilibrium. So the dynamics that are involved in the removal of the mantle lithosphere are unimportant. It's just that you're in a state of isostasy. Well, when I give, my son, now he's an academic, he gives talks, and I say to him, I said to him recently, well, when you get to the end, you don't show one of those really long, boring slides that has a list of all your collaborators and pictures of them, and you go down the list and all the funny ages and put people to sleep with all that. And he was quite sheepish in his reply, and he said, nobody remembers your last slide. So I'm going to give you, this is the last slide. If your auto mechanic doesn't understand Einstein's theory of relativity, should you care about dynamic topography? And I leave that to you to decide for yourself. Thank you.
Okay, first I just want to thank you for refreshing us with with analytical outlooks to life instead of just supercomputing models. It's refreshing and nice to see you came to these great conclusions without supercomputer. You mentioned the elephant and the wiggle, and at this point it sounds like you actually know the wiggle, or is it not wiggling? Or do you need more blind men on the problem?
I didn't have the elephant and the blind people in mind. That's a straight quote, and I don't know why von Neumann wanted to wiggle the elephant's trunk. The problem, obviously, though, is it takes five independent numbers for us to describe an extremely simple problem. And we've done this putting exponentially varying viscosity in the crust. That's another number. Put it in the mantle lithosphere. That's yet another number. You're up to 7. You compare that with the work that you criticized on my behalf. The number of numbers that you have to assume is so vast, and the number of runs you actually run so that okay, get pretty pictures. But I don't think we've made the elephant wiggle his trunk, but and we've already at 5 parameters. So I don't know what von Neumann would have done in our situation. He probably would have said this isn't worth studying. It's not relevant to the Earth, and he would have.
So having looked at this very carefully as you have now, is there great value, do you think, in continuing to measure how surface velocities are changing, especially in the vertical component?
Very good question. the solution I took for Morgan, it's limited in some ways. It has the assumption of a constant viscosity. It doesn't change much if you vary the viscosity structure. But the result that, at least for constant viscosity especially, that the surface deflection is independent of viscosity is unassailable, I think. But if you measured the rate of change of the surface height, that goes with the viscosity. In essence, you differentiate in there, and the canceled out in one case comes back in that case. So there's, I think, great hope that if we can measure, it's not rates of vertical motion, it's going to be rates of change of vertical motion, but in a sense, that's what one would get at if one had a present-day rate and one knew that 5 million years ago the rate had to be different. We might have a chance at using this to get at the viscosity structure. So I'm definitely a fan of vertical movement for that reason, as well as for a bunch of other questions. A bunch of other questions. If I gave the impression that I think vertical movements are dead and boring, I'm sorry, I misrepresented my view.
Okay, that's great. But how do we get the information that's reasonable for, say, 1 million years ago and 5 million years ago? I know that you've been trying to do this in Central Asia, but how do you actually get at it? Because I've seen very inconclusive results.
Yes, my guess is that when you get into the middle of the continent, we're going to be, right now, every method that's out there for getting a paleoaltitude has got 1,000-meter uncertainty. So in a million years, you don't change 1,000 meters anywhere. So you're not going to, that won't work. But I would think that coastlines would be a good place, because coastlines, you can see whether coastlines have gone up or not. And with that, you might be able to see a change in rate. And there's one in particular that I know of, the middle of the New Hebrides Islands, 3 millimeters a year is what the corals say. I'm sure there's a GPS instrument nearby. It might be possible to see whether that's a good estimate, whether that's what's happening today. And I would have the hope that going back with corals and other sea level measures, we might be able to get a longer geologic record. There are people, there's an example of this. This is work, people I know doing this, Maureen Ramo at Lamont, and she's working with a bunch of people, but there's an important person in there, Jerry Mitrovica. And they have a bunch of places where they think they have Pliocene sea level markers, the Pliocene shorelines that are different heights along the east coast of the United States. It goes up and comes back down. And they have these at different heights in different parts of the world. They have to correct for ice or lack of ice to put this in a proper reference frame. But they're seeing changes in height that are small. We're talking 30 meters, 40 meters, nothing. For me, that's noise. And that certainly could be dynamic. It is dynamic, probably. I think they have a hope of getting at this, getting at a rate. But it's going to take more clever geological thinking than I've been able to. That maybe I can, but I don't quite see how to go next with it. But there is the hope with shorelines of that kind. Certainly not abandoning, not at all. But no, not at all. But for questions of rates of change in height, I definitely would like to know how high was Tibet 10 million years ago, northern Tibet, or 15 million years ago, and I want to bet that it was lower. I want to bet at least 1,000 meters lower, and I would like someone to find that. But if whoever finds it finds that I'm wrong, I still would be nice to know. I can live with disappointment. I've been through this many times in my life. It's part of life. So I definitely haven't abandoned that. I think that's important. But with 1,000-meter uncertainty, there are only some questions you can ask. There are lots of questions you can't ask. So don't back in time, not over the short window that you have. The key is to well, I think there are different questions, but to go back in time for some questions, yes, absolutely, back 15, 20 million years for some of these. Same with the Rockies. It'd be nice to get more for that. But if the question were, do vertical movements tell us something about the internal structure of the Earth, like the viscosity structure, then a good rate now and a good average rate over some longer geologic period of time might put a good constraint on that. That might tell us something about it. This drops right out of the equations, and I'm not original in this. As I said, Maureen and Jerry Mitrovica and others are pursuing this. I haven't seen, I think I've seen anything yet. I worry that their models are too complicated and there are too many knobs that they could twist to get the answer. But it should be right there in the elementary physics of Morgan's solution, which is now nearly 50 years old. Probably is 50 years old because it probably took them a while to publish it.
I'm really glad you gave a talk on this topic. It was really informative. But I also wonder if you would say a few words about the other topics that Megan mentioned that you worked on, or one of them, say climate and topography.
Yeah, I have a talk that I give on that. It's kind of an embarrassing talk because, I'm interested in two questions. One is, why did we start getting ice ages? And I think the answer to that is islands popped up in Indonesia. And the other one is I care about how Tibet affects the monsoon. And that's how I got interested in climate, because the paleoclimatic data at the time really made it look like a change in Tibet happened simultaneously with the strengthening of the monsoon. And I think after 20 years, I won't say I wasted my time, but the premise was wrong. The monsoon didn't change 8, 9 million years ago, as people claim. It's a mistake. And the effect of Tibet on the monsoon is mild, but not insignificant. And there's a beautiful piece of work in the atmospheric sciences done 20 years ago showing or arguing that the reason the Sahara is dry and the reason the Mediterranean climate is what it is in summer it dries out because you heat over India. That sends Rossby waves westward, induces subsidence, and so you dry out the Sahara, you dry out the Mediterranean. Well, I would contend that eastern Tibet rose in the last 10 million years, and it caused Pakistan to dry out, for which there's paleoclimate data. So that's a problem that I'm working on. But as I said, if I had known what I know now, it was a lot of fun I wouldn't have had, but a lot of mistakes I wouldn't have made too.